A wonderful application of Newton's laws of motion is the pulley. The pulley changes the direction of the effort, and sometimes it even reduces the effort required to lift a body up. How do pulleys work? What forces act when a pulley works? We are going to learn about all this and more in this chapter called The Applications of Newton's Laws of Motion. Let's proceed. So first of all, what on earth is a pulley? A pulley is just a wheel over which a string can move. Something like this. So as you can see, there's a wheel here and the string is sliding over the wheel, isn't it? If the wheel is fixed, the pulley is called a fixed pulley. If the wheel is moving, then the pulley is a movable pulley. In this case, as you can see, the pulley is a fixed pulley because the wheel is fixed to this particular support from the roof, isn't it? Now what's the advantage of using a pulley? A pulley can be used to lift weights easily. This means that less effort is required to lift weights using a pulley. Let's see how. Take a look at this pulley here. This pulley is a fixed pulley and it has a mass M hanging from the string on the left. We in this case want to lift the mass M up by pulling the string on the right downwards. So we apply a force F on the string downwards, and as we do so, the mass M gets lifted up. How has our effort been reduced in this case? Has it been reduced at all? If you draw the free body diagram of the mass M, you will see that a tension force T acts upwards on this mass and the gravitational force mg acts downwards, isn't it? So T equal to mg. If you draw the free body diagram of the point on the string where we are applying the force, you will see that F minus T equal to 0, isn't it? We are here assuming that there is no acceleration in the pulley, that we are pulling this mass up slowly with constant velocity. So here F minus T is 0 because again there is no acceleration, we are just pulling the string with constant velocity downwards. So F equal to T and T equal to mg, isn't it? So F equal to mg. So the net force we have applied in pulling this mass upwards is mg. However, the actual force we would have had to apply in pulling the mass upwards if we did not use a pulley would also have been mg, isn't it? When you pull a mass upwards, the force mg acts downwards and you apply a force F upwards. So to pull the mass up with constant velocity or zero acceleration, you simply have to apply a force F equal to mg. So you can see that in this case, the pulley has not reduced the effort. The effort using the pulley was also mg and the effort without the pulley is also mg. But in this case, the pulley has helped us change the direction in which the effort is applied. In this case, we are applying the effort downwards, and applying effort downwards is easier than applying the effort upwards. This is because when we apply any effort downwards, we can put our weight on the string. We can use our weight and we can hold on to the string and pull it down easily. Applying a downward effort is quite easy compared to applying an upward effort. So in this case, the pulley changes the direction in which the effort should be applied, and that is how it makes lifting the mass M easier. Take a look at this pulley here, however. This one. In this case, the mass M is hanging from the wheel like this. This pulley is a movable pulley because the wheel is not fixed, isn't it? In this case, the right string is fixed and we will pull up from the left string like this. When we do that, the mass M rises up like this, isn't it? In this case, if you observe carefully and draw the free body diagram of the string, you will see that F is again equal to T. If you draw the free body diagram of the mass M, you will again see that in this case 2T is equal to mg. Why did I say 2T? You see, tension T is there in this part of the string on the left and tension T is there in this part of the string on the right. If you apply F equal to ma at this juncture where the two strings are meeting this third string, you will see that 2T acts upwards and the tension of the third string acts downwards, and since the net acceleration is 0, 2T is equal to the tension of the third string. So basically the tension here, the tension in the string that's holding the mass M up is 2T because of the two strings which are held on to this third string. Understood? 2T, the tension because of this string and this string, is equal to T1, the tension because of the third string, which is 2T. If you apply the free body diagram for the mass M, the net tension force upwards is 2T and the net gravitational force downwards is mg. So 2t equal to mg. When you solve these two equations, you get F equal to mg by 2. We already know that if we simply pull a mass m upwards, the net force required is mg. So in this particular case, the pulley is halving the force required to pull the mass m upwards, isn't it? We are applying the force upwards in this case also, but in this case, the force required is half of what the force required would be if you simply lift the mass m upwards with your hand. So there you go. In this case, the pulley is reducing the effort. So pulleys either reduce the effort required to pull a mass m up, or they change the direction of the effort, or they do both. You can attach the fixed pulley in the earlier case to this pulley, and if you use both pulleys at once, the effort will also be downwards and the effort will be halved also. So that's how pulleys are useful. They reduce the effort required. Here are some special points to keep in mind when solving problems related to pulleys and understanding pulleys better. The first point is that in our discussion of pulleys, we will assume that pulleys and threads are ideal. What does that mean? That means that the length of the thread is constant in this case. Understood? This means that you cannot stretch the thread. If you are pulling a mass m up and if you are pulling the thread down from the other side of the pulley, the thread won't get stretched, it won't get compressed, its length will be the same. So that is what we mean by an ideal thread. We will also assume that the pulley in this case is massless. It does not have any mass of its own. In fact, a lot of things change when pulleys start having masses. We will learn about pulleys with masses in a later chapter called rotation. Understood? For now, we will assume that pulleys don't have masses. Also, we will assume that the motion between the thread and the pulley is frictionless. Remember in the last chapter we had discussed that friction occurs whenever there is relative motion between two bodies. In this case, we will assume that the thread and the pulley have no friction between them and that their surfaces are smooth. So this is one other fact that we will assume here. Another interesting fact that we will assume is that the tension in the same thread is constant. You see, the tension in the same thread is constant if the thread is massless. We have already assumed that the thread is massless, the pulley is massless. So the tension in the same thread will also be assumed to be constant. So the tension force here on this block on the left will be the same as the tension force here on this block. So these are some assumptions that we will keep in mind as we solve problems related to pulleys in this chapter. Let's now move on and solve some problems. Let's try to find out the acceleration, of the 3m block and the 5m block in this case. Let's try to do that. The acceleration of the 3m block and the 5m block in this case will be the same. That is because the length of the thread is constant. So if the 5m block has an acceleration greater than the 3m block, then the thread must be stretched, isn't it? The 5m block has to move further away from the 3m block. That is not possible since the length of the thread is constant. So in these cases, when there is one thread connecting two blocks, the acceleration of the two blocks will be the same. Let's assume that the 3m block is going down with an acceleration a and the 5m block is going up with an acceleration a. Understood? It is obvious that if the 3m block goes down, then the 5m block must go up, isn't it? That is obvious. We are assuming here that the 3m block is going down. In reality, the 5m block can also go down, but in that case our answer will come out to be negative. Understood? So you needn't worry about exactly which direction this system is moving in. Is the 3m block going down and the 5m block going up, or is the 5m block going down and the 3m block going up? You needn't worry about all that. But what you do need to worry about is the fact that the acceleration of both the blocks is the same, and that if one block is going down, then the other block is definitely going up. Let's now consider the free body diagrams of both these blocks and write the equations. Let's first look at the free body diagram of the 5m block. A tension T definitely acts upwards on the block, and the force 5mg acts downwards on the block, the gravitational force. So we can write the equation T minus 5mg is 5m into a, isn't it? Net force is mass into acceleration. We have assumed that the 5m block is going upwards. We can similarly write the equation 3mg minus T equal to 3m into a for the 3m block, isn't it? After all, 3 mg is the gravitational force acting on it downwards and T is the tension force acting on it upwards. We have assumed that the 3m block is going downwards. So in this case, we have written 3 mg minus T is 3m into A. We have assumed that 3 mg is greater than the tension force T. Understood? In this case, you cannot write T minus 3 mg equal to 3m into A, because we have assumed that one of the blocks is going downwards and the other block is going upwards. Had we written T minus 3 mg equal to 3m into A, we would have had to write 5 mg minus T equal to 5m into A, because in that case we would have had to assume that the 5m block is going downwards. When we simplify these equations, we get the value of the tension force as 15 mg by 4 Newton, and we get the value of the acceleration of the blocks as 0.75 g meter per second square. As you can see, the value of the acceleration is negative. This is because our assumption was wrong. The 5m block is not going upwards, it is going downwards, and the 3m block is not going downwards, it is going upwards. So we have got the reverse direction of acceleration, isn't it? Acceleration is minus 0.75 g meter per second square, not plus 0.75 g meter per second square. So there you go. This is the value of acceleration here. By the way, there's another interesting method to solve this problem. You see, you can either draw the free body diagrams of each of the blocks and then you can apply F equal to ma for each of the blocks, solve the equations and get your answer. Or you can actually consider the entire pulley block system. You can stretch the string of the pulley in both directions, and you can imagine that the pulley block system is actually something like this. As you can see, there's this wheel of the pulley, and basically there's a string over the pulley, isn't it? So you can stretch the pulley strings, and you can imagine that you have a wheel in the middle, you have a string, and there's a mass 3m to the left, and there's a mass 5m to the right. You can then say that the net pulling force of the 5m mass is 5mg towards the right. You can say that the net pulling force because of the 3m mass is 3mg towards the right. Understood? This is simply an interesting way of understanding the pulley block system. You can then say that acceleration is net force on the pulley block system divided by the net mass of the pulley block system. The net mass of the pulley block system is 8m, and the net force on the pulley block system is 5mg minus 3mg, isn't it? We are assuming that the 5m block is pulling the pulley block system to the right with a force 5mg, its weight, and the 3m block is pulling the pulley block system to the left with its weight 3mg. So we can say that 5mg minus 3mg divided by net mass is the acceleration of the system, or the acceleration of the system is 5mg minus 3mg by 8m, which comes out to be 0.75 g. So you can calculate the net acceleration of a pulley block system by stretching the strings on both sides and assuming that the weight of the right block acts towards the right as a force on the total system, and the weight on the left block acts towards the left as a force on the net pulley system. Note that we haven't drawn any free body diagrams here. The 5m block is really not applying this net force on the system like this, but this depiction simplifies our calculation. In objective type problems, we can easily calculate what the net acceleration is very easily by using this special interesting technique. Understood? So whenever you're giving the pulley block system, you can stretch the string, you can assume that the right block is pulling the pulley system with a certain force, the left block is pulling the pulley system with its weight force, and the net force is equal to net mass of the system into acceleration of the system, isn't it? You can do that and you'll get your answer in objective type questions easily. For now, let's solve another problem. Find the tension in the string and acceleration of both the blocks in the figure shown. You can see what is happening here. There's a table, there's a mass m placed on the table, there's a string coming out of mass m, it goes over a pulley wheel, and then it comes down to a mass 2m that is hanging from the table. We have to find out the acceleration of both the blocks and the tension in the string. The acceleration of both the blocks will be the same because both the mass m and the mass 2m are connected by one single string, and so because the length of the string is constant, the acceleration of m and 2m must be the same. Let's first stretch the string as I just discussed and calculate the net acceleration of the system. That can be easily done. We know that the mass 2m is pulling the system down by a force 2mg. The mass m is not pulling the system anywhere, isn't it? Because its weight is not pulling the string. We have to calculate the weight that's pulling the string. So you can say that the net pulling force on the system is simply mass 2m's pulling force. That is 2mg. The net mass of the system is 3m. Therefore, the acceleration of the system is 2g by 3. We've calculated that so easily, isn't it? If you draw the free body diagram of the 2m mass, if you draw the free body diagram of the m mass, and if you solve the equations, you will again get the acceleration as 2g by 3. But this is just an easier method of getting the acceleration. You can now draw the free body diagram of the 2m mass to easily get the value of the tension force. We know that 2mg is the downwards force on the 2m mass and T is the tension force on the 2m mass upwards. So 2mg minus T is 2m into A. But we already know that the acceleration of the 2m mass is 2g by 3. So when you substitute A as 2g by 3, we get the value of tension force as 2mg by 3. Since the string is the same and it's a massless string, this is the tension force that also acts on the M block here. Understood? So there you go. Using our special interesting technique, we have solved this problem easily. For more problems and more explanations for the problems given, you can always log on to our website TopCoaching.com. The physics section has all the details that you need to know to solve competitive examination problems. Here's yet another example problem. So we are basically given this figure, and we are given that the pulley and the strings shown in the figure are smooth and of negligible mass. We are given two pulley wheels which are fixed to the roof. We are given this string. We are given two masses hanging from the two ends of the string. Understood? Now we are asked that if the system is in equilibrium, what should the angle theta be? So we basically have to balance forces, apply F equal to ma, and get our angle theta. Let's see what we will do. See, this is the system given. You can see that there is this mass m attached to a string going over a pulley wheel. Then again it comes in contact with the mass root 2m, which is attached to another pulley wheel. And then the string gets attached to another mass m. This system is in equilibrium. Let's consider this portion in the middle, the mass square root of 2 into m. Let's write the free body diagram of this mass here. If you consider carefully, you will see that a tension T acts here along the string at an angle theta to the vertical. A tension T again acts at an angle theta to the vertical on this mass root 2m. Since there are two strings here, you can say that the tension will be T. The tension will be the same in this case because there is only one string that's going from one end to the other end, isn't it? So the tension will be the same. However, since there are two portions of the string, you can say that two tension forces will act on the square root of 2 into m mass. The force acting downwards will be root 2 mg, isn't it? The gravitational force on the root 2 m mass. Similarly, if you consider the mass m on the left, for this mass, a tension force acts upwards and an mg force acts downwards, isn't it? This is the free body diagram. Now, we can write equilibrium equations for both these masses. For the mass root 2m, in the vertical direction, clearly root 2 mg, the net downward force, is equal to 2t cos theta, the net upward force. The net component of each tension force upwards will be t cos theta, and 2t cos theta will be root 2 mg for the root 2m block. Similarly, for the m block, mg equal to t. From both these equations, you can eliminate t and you will get the value of cos theta as 1 by root 2. That will give you the value of theta as 45 degrees. So there you go. We've got the answer. All we did was we considered each block in this case and we applied F equal to ma after drawing the free body diagram. Here's another problem. This one was asked in IIT JEE in 1984. The pulley arrangements of the figures are identical. The mass of the rope is negligible. In the first figure, the mass m is lifted up by attaching a mass 2m to the other end of the rope. So this is the figure given in the question. It's also given that in the first figure, the mass 2m attached to the right end of the rope pulls the mass m up. Understood? In the second figure, as it is shown, a force 2 mg acts on the right end of the rope and that pulls the mass up. Is the acceleration of m the same in both cases? So basically we are given this figure here. You can see that in the left case there's a mass m attached to the left and there's a mass 2m attached on the right. In the second figure there's a mass m attached on the left and a force 2 mg acts on the rope here. So we are asked, is the acceleration of mass m the same in both cases? It appears to be the same, isn't it? After all, the weight of the mass 2m is also 2 mg. In this case, we can use our special interesting technique, the technique of spreading our threads and calculating the acceleration of the blocks. When we use that technique, we see that the acceleration in the left pulley is 2 mg minus mg by 3m or g by 3. This is because the net pulling force in the case of the left pulley is 2 mg minus mg, isn't it? And the net mass being pulled is 3m, 2m plus m, 3m, isn't it? So the acceleration of both m and 2m masses is g by 3. If you stretch the string, then 2 mg force will act on the right, mg force will act on the left, and the net force will be 2 mg minus mg, and the net mass being pulled will be 3m. Now let's apply the same technique on the pulley on the right. For the pulley on the right, the net force acting on the pulley system will be 2 mg on the right string and mg on the left string, isn't it? When you stretch the string, 2 mg on the right and mg on the left. The net mass being pulled, however, is m. So therefore the net acceleration of the mass m in this case will be g, and g is definitely greater than g by 3. So accelerations are different in both cases. Understood? So you must understand that. Even though it seems like the accelerations are the same, when you calculate, you will see here that the accelerations are different in this case. So there you go. You must remember this. We have solved this question. Let's solve yet another one. It is given that this system shown is released at t equal to 0 seconds. What is the distance traveled by the m mass block in 5 seconds? As you can see, there's an inclined plane here, shaped in the form of a triangle. The system is released at t equal to 0 seconds. A force F equal to 10 t Newton acts on the rope on the right. What is the distance traveled by the mass m in 5 seconds? That's what we have to calculate. This question seems slightly complicated because the force acting here is a function of time. It is 10 t Newton. It isn't constant. Let's see what we can do. The first thing that we can do is that we can calculate the acceleration of the system. As you know, the acceleration of the system will be the same for all the blocks because all of them are connected by fixed inextensible strings, isn't it? This length of the strings cannot change, so the accelerations of all the blocks is the same. In this case, the net pulling force down the plane towards the right is F equal to 10t plus 3 mg sine 30 degrees minus 2 mg sine 30 degrees minus mg sine 30 degrees. The net mass being pulled is 3m plus 2m plus m, that is 6m. So when we divide the net pulling force by the net mass of the pulley block system, we get the value of the acceleration of the system, that is 5t by 3m meter per second square. If this sounds complicated, I'll explain it to you once again. You see, what we do is we stretch the string up like this, isn't it? When we do that, we look at the net weight with which each of the masses is pulling the system either towards the left or towards the right. The net force towards the right is F equal to 10t plus 3 mg sine 30 degrees, and the net force towards the left is 2 mg sine 30 degrees plus mg sine 30 degrees. Note that we have only taken the component of the weight that is along the plane, because that is the component, which is pulling the masses down the plane or up the plane. Understood? I know this might sound complicated, so you can close your eyes and visualize exactly how this is happening once again and you will get it. When you do that, you can see that the net pulling force is 10t plus 3 mg sine 30 degrees minus 2 mg sine 30 degrees minus mg sine 30 degrees divided by 6m. The acceleration is what we get now. The acceleration of all these masses up the plane and down the plane comes out to be 5t by 3m meter per second square. The acceleration of the 3m mass is down the plane, and the acceleration of the m mass and the 2m mass is up the plane. So there we have got the acceleration of these three masses. But we want to find out the distance moved by the mass m in 5 seconds. How do we do that? For that, we have to equate acceleration to dv by dt. You see, the acceleration is dependent on time, so we cannot use the equations v equal to u plus at, v square equal to u square plus 2as, and s equal to ut plus half at square. Those equations are valid only when acceleration is constant. Here acceleration varies with time. It is 5t by 3m. Therefore, you will have to use differentiation and integration. dv by dt is 5t by 3m. So v comes out to be 5 by 3m integral t dt, isn't it? So v comes out to be 5 by 3m t square by 2 plus c. This is the velocity of any of the masses at any time t, isn't it? It is given, however, that the masses are at rest at time t equal to 0. So v is 0 when t is 0. Therefore, v comes out to be 5 by 3m t square by 2. Now we want a relationship between the displacement of each mass and the time, isn't it? After all, we want the distance covered by mass m in time t. Therefore, we put v equal to dx by dt. dx by dt is 5 by 3m into t square by 2. Again, when we take dt to the other side and integrate, we get this expression. X equal to integral 5 by 3m t square by 2 dt. On integration and on applying the condition that x is 0 at t equal to 0, we get the value of the distance covered by mass m in 5 seconds as 625 by 18m meters. Understood? So there you go. That's how we get our answer. What we did in this question was, we used the pulling force method to first obtain the acceleration of all the masses. Once we got the acceleration, we put acceleration equal to dv by dt. And then we put velocity, which we got as a function of time, as dx by dt. We thus got a relationship between x, the displacement of the mass m at time t, and t. Then we put t equal to 5 seconds to get the value of the displacement of mass m at t equal to 5 seconds, which came out to be 625 by 18m meters. So there you go. That's our answer. So now that we've solved so many pulley problems, let's move on to the next concept, thread constraint. Of course, you can always solve more problems and attempt more tests related to pulleys at TopCoaching.com's physics section. So what is this thread constraint? Thread constraint simply means that the length of each individual thread is constant. You see, what happens is, when we are solving some pulley problems, especially those involving movable pulleys, we write all the equations. We draw free body diagrams for each moving body, and we write F equal to ma equations for all the bodies. But still, we do not get the answer. It hasn't happened to us in the previous questions, but it does happen at times. It happens when there are movable pulleys involved. In that case, we have to apply a special equation called thread constraint equation, which establishes the fact that the length of each thread is constant. This gives us an extra equation which helps us solve all the other equations and get our acceleration and tensions correct. Understood? So thread constraint basically gives us an extra equation if we are not able to find out our acceleration or tension by using all the other equations. Even after applying F equal to ma for each body involved, if we are not getting the answer, we need the thread constraint. Of course, thread constraint is generally used when the pulley itself is moving. Take a look at this system. Let's try to write the thread constraint equation for this system. As you can see, there are two pulleys in this system. One pulley is a fixed pulley and the other pulley is a movable pulley. This one is a movable pulley, isn't it? From which masses 2 and 3 hang. Now, first we choose a fixed point in the system. What is the point in the system that does not move at all? We choose that point. In this case, the fixed point is this point, this wooden block that you see on your screen, this one. After all, it is attached to the fixed pulley and it does not move, isn't it? So this is our fixed point. Now we write down the coordinates of each moving point in the system with respect to the fixed point. So what are the moving parts of this system? The block 1 is a moving part, block 2 is a moving part, the block 3 is a moving part, and the moving pulley is also a moving part. So there are these 4 moving parts in the system. We write down the coordinates of each of these moving parts. Here, LP denotes the position of the moving pulley from the fixed point. So we've drawn an arrow from the fixed point to the moving pulley, and we've said that LP vector here represents the position vector of the pulley here. L3 vector here represents the position vector of mass 3. L2 vector here represents the position vector of mass 2. And L1 represents the position of mass 1. So basically we've considered a fixed position line here, and then we've drawn the different position vectors of each moving part of the system. L1, L2, L3 and LP. Now we will apply the thread constraint. The thread constraint says that a length of a single thread which is inextensible is constant. Which thread length is constant here? This thread length is constant here. The thread that joins mass M1 to the movable pulley is one single thread. Its length is constant. So we can say that length of first thread equal to constant, or L1 plus LP equal to constant, isn't it? The distance of mass 1 from the fixed point plus the distance of the pulley from the fixed point is equal to the length of the first thread, which is constant. So that is the first thread constraint equation here. If we differentiate this equation with respect to time, we will see that dL1 by dt basically represents the velocity of mass 1 with respect to time. Similarly, dLp by dt represents the velocity of the pulley here, the movable pulley, with respect to time. So v1 plus vp is 0. If we further differentiate this equation, we get a1 plus ap equal to 0. So acceleration of mass 1 plus acceleration of the moving pulley is 0. So there you go. By applying the first thread constraint equation, we have derived the equation a1 plus ap equal to 0. So this is one important thing. In this case, do remember that a1 represents the downward acceleration of mass 1, because the acceleration will be in the same direction as the position vector of mass 1, isn't it? We are differentiating the position vector to get the velocity and acceleration. So a1 represents the acceleration of mass 1 downwards, and ap represents the acceleration of the movable pulley downwards. So a1 is minus ap. Now this is the first constraint equation here. Let's now write the second constraint equation. The length of the second thread is also constant. What is the length of the second thread, the thread connected to the movable pulley and the thread joining mass 2 and mass 3? The length of this second thread is L2 minus LP. L2 minus LP represents this thread plus L3 minus LP, isn't it? L2 minus LP represents this left portion of the thread, and L3 minus LP represents the right portion of the thread. This length is constant. Or you can differentiate this equation and say that V2 plus V3 minus 2Vp is 0, or A2 plus A3 minus 2AP is 0, isn't it? Here A2 represents the acceleration of block 2 downwards, A3 represents the acceleration of block 3 downwards, and AP represents the acceleration of the movable pulley downwards. So here, this is the second constraint equation that we have got, isn't it? So there you go. These are the two constraint equations that we have obtained. So now if we draw free body diagrams of mass 1, 2 and 3, and then we apply these constraint equations, we will get our answer. Otherwise, if we write down the free body diagrams of masses 1, 2 and 3, we will not get our acceleration answers despite writing all the correct equations. So we need the constraint equations, the extra equations, to get our answers here. Understood? So there you go. All we did was we saw how many threads there are. There are 2 threads. We wrote down the constraint equation for the first thread, and then we wrote down the constraint equation for the second thread. We denoted each movable part of the system by a position vector, and then we just applied the equation. The length of the first thread is constant, the length of the second thread is constant, and thus we got the relationship between the different accelerations involved. All this might seem complicated at first glance, so let's solve a problem to get our concepts clear. Find the acceleration of the block of mass 1 kg that is on the table. The table is frictionless and smooth. The pulleys are massless and ideal. The thread is also ideal. This picture shows a table and a mass of 1 kg on the table. This mass of 1 kg is attached to a fixed pulley that is attached to the table. This pulley's thread now goes on and gets attached to a movable pulley here, which has a mass of 2 kg attached to it. And then this movable pulley is attached to yet another movable pulley which has two masses of 1 kg and 3 kg attached to it. We have to find the acceleration of the mass of 1 kg that's on the table. What do we do? Well, let us first write down the constraint equations in this case, since movable pulleys are involved. First of all, we have to choose a fixed point. What is the fixed point in the system? Well, this pulley here, the pulley that is fixed, definitely that's a fixed point. So we can define the coordinates of all the other masses by using the fixed point here. The position of the 1 kg block with respect to the fixed point is L1 to the left. The position of the first pulley is LP1. Now, using just these two parameters L1 and LP1, we can say that the length of this first thread is constant. You see, there are three threads here. This thread, the thread joining the 1 kg block to the movable pulley, the second thread joining the 2 kg block to the second movable pulley, and this third thread joining the 1 kg and 3 kg block. So there will be three constraint equations. We can apply the first constraint equation for the first thread using only L1 and LP1. The first constraint equation is that L1 plus LP1 is constant, isn't it? When we double differentiate this equation, we get A1 plus AP1 is 0. Note that in this case, A1 is assumed to be the acceleration of the 1 kg block towards the left, and AP1 is assumed to be the acceleration of the first pulley downwards. Understood? So A1 plus AP1 is 0. We can now apply the constraint equation for the second thread. For the second thread, these are the important parameters involved. As you can see, L2 minus LP1 plus LP2 minus LP1 is constant, isn't it? L2 minus LP1 is the same as the left portion of this thread that holds up the 2 kg block, and LP2 minus LP1 is the portion of the thread that joins these two movable pulleys, isn't it? LP2 here represents the position of the second movable pulley, and LP1 represents the position of the first movable pulley from the fixed pulley. Differentiating this equation, we get A2 minus AP1 plus AP2 minus AP1 equal to 0. Note here that A2 is the acceleration of the 2 kg block downwards. AP1 is the acceleration of the movable pulley downwards. AP2 is the acceleration of the second movable pulley downwards. So there you go, we got our second constraint equation. We can now apply our third constraint equation. As you can see, in this case, L3 minus LP2 plus L4 minus LP2 equal to constant. As you can see, the length of the third thread is constant. So the left portion of the thread that joins the 1 kg block and the movable pulley is L4 minus LP2. The second portion of the thread is L3 minus LP2. So therefore, since this is constant, we can say that A4 minus AP2 plus A3 minus AP2 is 0. Here A4 is the acceleration of this 1 kg block downwards, A3 is the acceleration of this 3 kg block downwards, and AP2 is the acceleration of the second movable pulley downwards, isn't it? So this is the third constraint equation. So there you go. We have 3 threads and we have now obtained 3 constraint equations. Now that we have obtained the constraint equations, we can draw the free body diagrams of each portion here and apply F equal to ma. Let us first draw the free body diagram of this first movable pulley here. The tension upwards is T1 and the tension downwards on both sides of this movable pulley is T2, isn't it? I have written T2 twice because this thread is the same, but one portion of the thread is applying a tension T2 on the pulley and the other portion of the thread is also applying a tension T2 on the pulley downwards. T1 equal to 2T2. That's the equation we get here. we can now draw the free body diagram of the second movable pulley. In this case, the tension upwards is T2 and the tension downwards is T3. Note that this T2 is the same as the T2 that was acting downwards in the case of the first pulley. Remember, there were two T2 tensions acting downwards in the first pulley. This is the same T2 because the same thread has the same tension. So there we get T2 equal to 2T3. Here T1 is the tension in the first thread, T2 is the tension in the second thread, and T3 is the tension in the third thread. We can similarly apply the equation F equal to ma for the 3 kg block in the vertical direction. The tension upwards is T3 and the net force acting downwards, the gravitational force, is 3g, and if g is 10 meter per second square, the net force acting downwards is 30 Newton. By applying the equation F equal to ma, we can say that 30 minus T3 is 3 into A3. Here we are assuming that the acceleration A3 is downwards. Similarly, we can apply the equation F equal to ma for the mass of 1 kg. Tension T3 acts upwards and a force of 10 Newton equal to the weight of the 1 kg mass acts downwards. In this case again, we can apply the equation 10 minus T3 equal to A4. Note that in this case, I have written 30 minus T3 equal to 3A3 and 10 minus T3 equal to A4. So I have assumed that both the blocks are going down in this case. Why have I assumed that? Actually, in this case, I have already assumed that A3 is acting downwards and A4 is acting downwards. Remember when we wrote the constraint equation, we assumed that all accelerations are downwards, isn't it? So that is the reason I have assumed that 10 is greater than T3 and 10 minus T3 is A4, and that 30 is greater than T3, that 30 minus T3 is 3A3. Understood? To make sure that the sign of acceleration is the same, the sign of A3 is the same as the one that I chose earlier when writing the constraint equation, I have written my equations this way. So you must keep in mind the direction that you have used as positive when writing the constraint equations must also be taken into account when you're writing the F equal to ma equations after drawing the free body diagram of each movable part of the system. Understood? So there you go. We can similarly write the F equal to ma equation for the 2 kg block. In this case, 20 minus T2 is 2A2, isn't it? So there you go. We have got so many equations in this case. We've got these constraint equations, 3 of them. Then we've got these tension equations. And then we've got these F equal to ma equations, so many of them. All these might sound difficult, but using a bit of substitution here and there, you can solve these equations easily. When you solve these equations, you see that there are 8 equations and 8 unknowns. And therefore, when we solve these equations, we get the value of A1, the acceleration of the 1 kg block towards the left, as minus 1620 divided by 19 meter per second square. Understood? Note that in this case, A1 was taken to be positive towards the left. So A1 being negative means that the acceleration of the 1 kg block is towards the right, and it is equal to 1620 by 19 meter per second square. In these cases, when you're applying the thread constraint equations and you're also drawing free body diagrams and applying F equal to ma, do make sure that accelerations are positive in the direction in which the position vectors are taken. Understood? So when you first draw L1, L2, L3 and the positions of different moving bodies from the fixed point, the direction in which you draw that position vector, that is the direction in which accelerations are taken to be positive when you're applying constraint equations. Understood? So in this case, A1 comes out to be minus 1620 by 19 meter per second squared to the left. That's our answer. All this might seem a bit complicated. So for more practice and to attempt more tests related to constraint equations, log on to our website TopCoaching.com. Here's an interesting fact, by the way. If you have a moving pulley and if you have a block dangling at the left end and a block dangling at the right end of this movable pulley, in that case, the acceleration of the pulley will be half of the sum of accelerations of the first block and the second block. Understood? This is a very important fact that is very, very useful in competitive examinations. So in this case, the acceleration of the pulley is a1 plus a2 by 2. If a1 is the acceleration of the block on the left and a2 is the acceleration of the block on the right. You can easily derive this expression by applying constraint equations and applying the fact that the length of this thread is constant. Understood? So AP is a1 plus a2 by 2. Try deriving that yourself, this expression. Try writing constraint equations and try deriving the relationship between a1, a2 and ap. You will get this answer easily. Here's another example problem. A force F is applied on the object of mass m as shown. Calculate the acceleration of mass m in the adjoining diagram. All the surfaces are frictionless. So as you can see, we are given this figure here. There is a block of mass m dash. There are these three pulleys connected to the blocks. There's a block of mass capital M and the block of mass small m placed over the block of capital M mass. A force F is applied on the block of mass capital M towards the right. We have to find out the acceleration of the mass small m. Understood? So what do? Well, we do what we have been doing all along. We draw free body diagrams for each moving point shown in this figure, and then we apply a constraint relation that mentions that the length of this one thread used in this diagram is constant. Understood? Let's first draw the free body diagrams. Let's draw the free body diagram of the small mass m. Let's say a tension T acts towards the left. Therefore, for this small mass m, T is equal to m into am. We have assumed that am is positive towards the right. Therefore, I have written minus T is m into am. Note that you can also write T equal to m into am, but in that case you will have to assume that the acceleration am is towards the left. Understood? Now we can write the free body diagram of the capital mass m and the pulleys connected to it, this portion. If you look at this portion, you will see that there are 4 tension forces acting, isn't it? You see the tension force throughout the thread is the same. But since 4 portions of this thread are attached to these fixed pulleys attached to the mass m, you can say that the net force towards the right is 4T. So 4T is minus m dash into am dash. Understood? Again, in this case also, I have written minus m dash into am dash because I have assumed that am dash is towards the left. Understood? So you can write 4T equal to m dash into am dash also, where am dash is the acceleration of the block m dash. But in that case, you will have to assume that am dash is towards the right. Understood? In this case, I have specifically assumed that am dash is towards the left. So we have these 2 particular equations here. We can now draw a free body diagram for this point, the mass m. A force F acts on the mass m towards the right, and 2 tension forces 2T act on the mass m towards the left. Again, the tension throughout this string is the same, but since 2 portions of the string are attached to mass m, I have written 2T as the force that acts on mass m towards the left. I have written F minus 2T equal to capital M into am, isn't it? Net force is mass into acceleration. In this case, I have assumed that am, the acceleration of the mass m, is towards the right. So I have basically assumed that the acceleration of the small mass m and the acceleration of capital mass m is towards the right, and I have assumed that the acceleration of m dash is towards the left. Doing so helps me with writing my constraint equation. I will write the constraint equation considering the fixed point to be this particular point, this triangle made of wood that is placed here. After all, this point is fixed. The moving points are Lm dash, the position of m dash, Lm, the position of small m, L capital M, the position of capital M. These are the special moving points. Note that I have already assumed the accelerations in the direction of these position vectors, to make it easier for me to write the constraint equation. I have already assumed that the acceleration of m dash is to the left, the same as the direction of Lm dash, the acceleration of small m is to the right, the same as the direction of Lm, and the acceleration of L capital M is to the right, the same as the direction of L capital M. So now the length of this thread is constant. So you can see that 2Lm plus 4Lm dash plus L small m is constant, isn't it? There is no doubt about it. This length is 2Lm here, this length is 2Lm dash here, this length is also 2Lm dash here, and this length is L small m here. So 2L capital M plus 4Lm dash plus Lm is constant. By double differentiating this equation, we get 2Am plus 4Am dash plus Am equal to 0. This is the constraint equation in this case. So we have 4 equations and 4 variables. We don't know Am, Am dash, A small m and T, isn't it? But we have all these 4 equations. On solving these 4 equations, the value of A small m comes out to be 2m dash f divided by 4m into 4m plus m dash plus mm dash. So this is the value of the acceleration of the block of mass small m. Understood? So there you go. By simply writing the constraint equations and by writing the F equal to ma equations for each block here, we have found out the value of the acceleration of the block of mass small m. Up till now, we were observing all the bodies, that we talked about, like pulleys, blocks, strings, from a ground frame of reference. So basically we were standing on the ground and then we were looking at the forces acting on a block, or the force acting because of a thread, or the force acting on a pulley. However, what if we don't observe our system from an inertial frame of reference? What if we observe our system from a body that's already accelerating? Let's say I'm sitting in this bus and now I'm observing a pulley system. The pulley system could be inside the bus or outside the bus, but I myself am moving. The observer who is observing the forces is himself accelerating. How do things change in that case? Let us say I am observing a system by sitting in this bus which is accelerating with an acceleration A. Now if I have a block placed inside this bus and I have to study the motion of that block, then apart from all the other forces acting on the block, I will have to apply an extra force ma in a direction opposite to the direction of the acceleration of the bus. Understood? Here m is the mass of the block and a is the acceleration of the bus towards the right. So did you understand what I just said? If we observe the motion of bodies while we are ourselves in a non-inertial frame of reference, in a frame of reference that is accelerating, then we have to apply a special force called pseudo force in the direction opposite to the acceleration of our frame of reference. Understood? This force is mass into acceleration, where mass is the mass of the body being studied and acceleration is the acceleration of our frame of reference. And this force, that we apply on different bodies when we are observing them from a non-inertial frame of reference is called pseudo force. I know all this sounds really complicated, so let me give you an example. Take a look at this trolley moving on the road. As you can see, a pendulum bob is hanging inside the trolley. This pendulum bob is tilted at an angle with the vertical. It's tilted at an angle theta and it is at rest with respect to the trolley. So we can find the angle theta here with the help of pseudo forces. Now let us consider the different forces that are acting on the bob. The tension force is of course acting at an angle theta with the vertical, isn't it? It's acting along the direction of the string. The force mg is acting downwards. Now since we are observing the pendulum from the frame of the trolley and the trolley is itself accelerating, we will have to apply a pseudo force on the pendulum bob. Understood? When we do that, we will get all our values and our accelerations, our velocities, everything in the frame of the trolley. So we apply a pseudo force on this pendulum bob. The pseudo force acts towards the left because the acceleration of the trolley is towards the right. The pseudo force is m into a, where m is the mass of the pendulum bob and a is the acceleration of the trolley. So you can see that these are net forces on the pendulum bob when observed from inside the trolley, when observed from the frame of the trolley. Understood? So whenever you observe any body from a non-inertial frame, you will have to apply a pseudo force on that body. The direction of the pseudo force will be opposite to the direction of acceleration of your frame of reference, and the pseudo force will be equal to m into a, where m is the mass of the body and a is the acceleration of your frame of reference. When we balance our equations, we see that T cos theta is mg, isn't it? In the horizontal direction, the component of tension is T cos theta. In the vertical direction, the component of tension is T cos theta, so T cos theta is mg. In the horizontal direction, the component of tension is T sin theta, and T sin theta and ma act in opposite directions, so T sin theta is ma, or tan theta is A by G. Understood? So there you see that this bob is in equilibrium in the frame of the trolley, and the angle which it makes with the vertical is A by G, where A is the acceleration of the trolley and G is the acceleration due to gravity. Understood? So this is the concept of pseudo force. This concept is actually very similar to the concept of relative acceleration and relative velocity that we studied earlier. Remember when we had to study the velocity of a body from an accelerating frame of reference or a moving frame of reference? We used to bring the moving frame of reference to rest by adding an opposite velocity or an opposite acceleration to our frame of reference. Remember we had attempted many such problems in the chapter of relative velocity? Similarly, we add an opposite force called pseudo force to any body when we observe that body from an accelerating frame of reference. We bring our very own trolley to rest by adding an opposing force to our trolley, and we apply an opposite acceleration to our own trolley frame to bring it to rest, and then we apply the same opposite acceleration to the other body which we are observing, and this acceleration multiplied by the mass of the body is the pseudo force. As we solve more problems, you will understand more about pseudo force. Of course, for more detailed explanations of pseudo force and for more examples, do log on to our website TopCoaching.com. Here's an example problem related to pseudo force. A wedge of mass m with an angle of inclination alpha rests on a smooth horizontal surface. A bar of mass m is placed on the wedge. Assuming friction to be negligible, find the acceleration of the wedge. So well, what's up in this question? We are given a wedge. The wedge has a mass capital M. Its angle of inclination is alpha, and we are given a small block of mass m placed on the wedge. We have to find out the acceleration of the wedge. This question can easily be solved by the concept of pseudo force. What we can do first is, of course, what we again have to do is that we have to draw the free body diagram of the mass capital M, we have to draw the free body diagram of the mass small m, and we have to apply F equal to ma. However, in this case, it will be easier for us to draw the free body diagram of mass small m in the frame of reference of the wedge. Understood? Otherwise, it will be very difficult to study the motion of mass small m with respect to the ground frame. In the wedge frame of reference, these are the forces that act on the mass small m. The normal reaction acts perpendicular to the slope of the wedge. The force mg acts downwards. We are assuming that the acceleration of the wedge is a towards the right. Since the acceleration of the wedge is a towards the right, we are applying a pseudo force ma on the small mass m towards the left. There you go. Now we can balance the forces. We know that the small block mass m moves only parallel to the slope of the wedge. It does not move perpendicular to the slope of the wedge. So perpendicular to the slope of the wedge, the net force is 0. Or you can say that mg cos alpha plus ma sin alpha equal to n. Mg cos alpha is the direction of the gravitational force on the small block mass m perpendicular to the wedge. Ma sin alpha is the direction of the pseudo force perpendicular to the wedge, and both these forces balance the normal reaction. Parallel to the wedge, we can say that mg sin alpha minus ma cos alpha equal to mam, where am is the acceleration of the small block mass m in the frame of reference of the wedge capital M. Again, mg sin alpha is the component of the gravitational force along the slope of the wedge, and ma cos alpha is the direction of the pseudo force along the slope of the wedge. Mg sin alpha minus ma cos alpha is m into am. We can similarly draw the free body diagram of the wedge of mass capital M and write equations for this wedge. You can see that these are the forces acting on the wedge. The normal reaction from the small block mass m acts on the wedge perpendicular to the slope of the wedge at an angle alpha with the vertical. The weight of the wedge mg acts downwards, and the normal reaction n1 from the ground acts upwards. In the horizontal frame of reference, you can see that the net force is n sine alpha. We have assumed that the net acceleration of the wedge is towards the right. So we can say minus n sine alpha, the net horizontal force on the wedge, is capital M into A. Note that I have written minus here because we have already assumed that A is towards the right, isn't it? Now we already have these equations. Mg cos alpha plus Ma sin alpha is n, and Mg sin alpha minus Ma cos alpha is mam. When we solve all these equations, we get the value of A, the acceleration of the wedge, as this expression. It comes out to be minus capital Mg sin alpha cos alpha divided by m plus small m sin square alpha. This is the value of the acceleration of the wedge. The minus sign here tells us that the acceleration of the wedge is actually towards the left and not towards the right. That is obvious also because the only horizontal force on the wedge is n sin alpha, which is acting towards the left, isn't it? So obviously the wedge will get accelerated towards the left. That is why there is this negative sign in front of this expression. So all that we really did in this question was we applied F equal to ma in the horizontal and vertical directions for the block of mass small m, and we applied F equal to ma in the horizontal direction for the wedge. Of course, when we considered the block, we considered the pseudo force as well, and we calculated the acceleration of the small block of mass m in the frame of the wedge. That made balancing forces easier. Here's yet another question. What is the acceleration of the mass m with respect to the wedge in the figure above? All the surfaces are frictionless, the pulley is massless, and the thread is ideal. So basically this is what is given in the question. We are given a wedge of mass capital M, and we are given a small block of mass m which is placed over the wedge. The wedge itself is connected to a pulley, and it is also connected to a small block of mass m that is dangling vertically, isn't it? We have to calculate the acceleration of this block m which is placed on the wedge with respect to the wedge. What do? Of course, we again balance forces and apply F equal to ma. Let's consider the small block of mass m that's placed on the wedge first. Let's assume that the wedge gets accelerated towards the right with an acceleration a. In that case, a pseudo force m into a will act on this small block of mass m towards the left, isn't it? Of course, the normal reaction because of the wedge will act perpendicular to the slope of the wedge, and the weight of the block mg will act downwards. Let's balance these forces parallel to the slope of the wedge and perpendicular to the slope of the wedge. Parallel to the slope of the wedge, we have mg sin alpha minus ma cos alpha equal to m into am. Of course, parallel to the slope of the wedge, the forces are mg sin alpha because of the weight and ma cos alpha because of the pseudo force, and acceleration of the block of mass small m is am with respect to the wedge. Perpendicular to the slope of the wedge, the block of mass small m is at rest. So mg cos alpha, the component of the weight perpendicular to this plane, plus ma sin alpha, component of the pseudo force perpendicular to the plane, is equal to n, the normal reaction on the block of mass small m. We can similarly apply F equal to ma for the wedge. In the case of the wedge, you can see that a normal reaction N1 from the table acts on the wedge. The weight of the wedge, capital Mg, acts downwards, and the normal reaction N from the block of mass small m acts perpendicular to the slope of the wedge. The tension T also acts towards the right on the wedge, isn't it? Applying Newton's second law of motion in the horizontal direction, we get T minus n sin alpha equal to capital M into A. Here A is the acceleration of the wedge, isn't it? There's no doubt about it. N sin alpha is the component of the normal reaction in the horizontal direction. We don't have to write the equation in the vertical direction because that involves N1, and we don't want an extra variable N1 being involved. We can now apply the equation F equal to ma for this block of mass small m. When we do that, we have the force mg acting on this block downwards, and we have the tension force acting upwards. So we can say that mg minus t is m into a. So we have so many equations here. We have the equation we get when we balance forces perpendicular to the plane for the block of mass small m. We again apply F equal to ma for the block of mass small m parallel to the plane. We apply the equation F equal to ma for the wedge in the horizontal direction, and we just applied mg minus t equal to m into a for the block of mass small m that is coming vertically downwards. So solving all these equations, we get the value of am, the acceleration of the block of mass small m that's placed on the wedge parallel to the slope of the wedge, as mg sin alpha into 1 minus cot alpha into m minus m sin alpha cos alpha divided by capital M plus small m sin square alpha. I know this is a very complicated expression, but once you simplify all these expressions, this is what you get. Of course, in this question we have assumed that the acceleration of the wedge of mass capital M and the small block of mass small m that moves vertically are one and the same, because both of them are connected to the same string, isn't it? So all we did again was we applied Newton's second law of motion by drawing free body diagrams of different bodies. That is all you have to do in most questions related to the laws of motion. So there you go. I hope you have understood pseudo forces now. That brings us to the end of this chapter related to pulleys and pseudo forces. Let's move on to the next chapter related to friction.